Okay, let's get started. So any question from this time? So this time we go over pretty fast about this block diagram interconnection and the analysis with them about LTI system. I think analysis with system function. And I guess we go over pretty fast, so we will not ask you to do too much detail about it. But I think the bottom line is if you are given an interconnection system, you should be able to write down this interconnect system with the possible feedback. Then you should be able to write down this system function analysis. So you should be able to write down system function of each line and write down equation of them and solve out for this effective system function of the whole interconnect system. And I think this should be pretty straightforward. So when you go through a block, you multiply the system function together. And when you have forking, then each line are the same. And when you have addition, you add each one together and kind of solve the system function here and solve the equation here and solve for what's the output big Y related to input big X. Okay? Oh, sorry. Okay, yeah. And that's a very quick review of last time. Today we are going to go to this next topic that we have done a little bit last time. And that's the unilateral Laplace transform. Okay, and stated last time. So unilateral Laplace transform is another form of Laplace transform that's very similar to what we do, but they change the integration period from integration range from this 0 minus. So instead of integrating from minus infinity, you're integrating from 0 minus. And so effectively you only pick out the x of t starting from t at 0. And the minus sign means that we're also picking out all the singularity of x of t at t equals 0. So in particular, you have a delta function, then you will have a non-trivial unilateral. Okay, okay, I think we need to wait a little bit. Yeah. In particular, if we have a delta function as x over t, then this is 0 minus will also pick out the delta function. Okay. Yes. Hopefully you can still hear me. Yeah. Yeah, and I've seen some example of this unilateral Laplace transform, and in particular, yeah, I already tried that, but这边的喇叭吗？是有可以把它关掉的地方吗？没有。好，有可以把麦克风关掉的地方。还是可能同学坐离他远一点会比较好吗？我不太确定。可能 iPad 的我不太确定。我看一下这里有可以调控的吗？我这里没有可以调控的地方。对。或者我可能要试着再把 iPad 关掉之类的吗？我不太确定，因为其实不是我的这里造成干扰，可能是大家的电子产品的网络可能试着关机这样子。OK， 是可以把我自己 WiFi 没有插掉。对，我们等待一下看会比较好吧。所以先试，这大家勉强也可以听得到吗？还是有电子产品的同学可能先试着关机一下。OK， 好吧，Anyway, I guess let's try to keep going. So so we have this unilateral Laplace transform, and we have seen this example. Okay, so example of those functions. If our x of t is this t to the some power times e to the minus at u of t, then we know its bilateral Laplace transform is 1 over s plus a to the nth power. Those are very useful for doing partial fraction expansion and so for inverse Laplace transform. Okay, and we see that those functions they are equal to 0 when t less than 0 because of the u of t. So we see that the unilateral Laplace transform is the same as the bilateral Laplace transform because the integration will be the same for either you integrate from minus infinity or 0 minus. Okay, so that's the same. And the important part we see that is for unilateral Laplace transform, we don't really need to specify its ROC because you cut off x of t at t equal to 0. So your x of t is always right-sided signal, and so your ROC will always be a right-hand plane. So your ROC will always extend to right infinity. So you can just pick the ROC as a right infinity part. Okay, it's not going down. 可能请同学是不是坐离他远一点，看会不会好一点？对，请同学稍微移一下位置，就到另外一边的话，看会不会干扰比较少。试试看，抱歉，谢谢。有比较好吗？差不多。OK。Yeah. Okay, so that's the unilateral Laplace transform of that gives you those partial fractions. And then we see an example where you do a shift on those functions. So instead of just exponential decay and u of t plus 1, okay, it's getting a little better. Instead of just exponential decay starting at t equals 0, if you do a time shift so that your exponential decay is starting from time equal to -1, then now the unilateral Laplace transform and the bilateral Laplace transform will be different. So in this example, the bilateral Laplace transform you can just get from this time shift formula. So you get this HRE to the s factor. But for unilateral Laplace transform, you get e to the minus a factor. So e to the minus a is different from e to the s. So yeah, because the HR is the HR signal from -1 to 0, the unilateral Laplace transform will not pick up. Okay, and now let's see another example that we didn't have this time. So example we have that now we have this weird example where we have a lot of singularity. So we have x of t equal to delta of t plus 2u of t plus u1 u of t. And okay, and then once again we see that the signal is equal to 0 for t less than 0 because we have these two singular functions at t equal to 0 and e to the t u of t. That's cut off t equal to 0. Okay, and so once again the unilateral Laplace transform should be same as the bilateral transform. Okay, and then we just use the table for the bilateral Laplace transform. We have the transform of delta of t and u1 of t, and they actually transform to very easy equation. So delta of t will transform to 1, and u of t will transform to s. So they are just power of s. And so you just have the transform being 1 plus 2s, and this e1 e of t u of t will transform to 1 over s minus 1, and so this is your bilateral Laplace transform, and this is also your unilateral Laplace transform. Okay. And finally it's getting to sense. Okay. Well. That was very annoying, but any questions so far? Are people able to hear about this? Okay. Yeah. Sorry about the interruption. Okay, and now we go to next example. And we have this unilateral Laplace transform of rational function. This is also something we like a lot. Okay, when we do bilateral Laplace transform. So big X of S equal to 1 over S plus 1 times S plus 2. Okay? And we know how to do the, and for this we want to do this difference. So we are given unilateral Laplace transform here, and we want to get its inverse. Okay? And so one thing we see here is that we didn't say RLC of this thing. For bilateral Laplace transform, so this thing has a pole at s equal to -2 and a pole at s equal to -1. And for bilateral Laplace transform, we know it has 3 possible RLC. But for unilateral Laplace transform, we don't need to specify RLC because we know the RLC is always the s bigger than 1 part. It's always a right-hand plane. So we know that RLC must be this one, and we can just pick RLC being this one. And so RLC is s greater than real part of s greater than -1, and then we can have the unilateral Laplace transform exactly inverted as the bilateral Laplace transform inversion. So you have this being 1 over s plus 1 minus 1 over s plus 2 doing partial fraction expansion, and picking both of the partial fraction inverted to the right side. So you have this e to the minus t times u of t minus e to the minus 2t u of t, and yeah, this is for t greater than 0 minus, because the unilateral Laplace transform only care about t greater than t greater than 0. Okay, and any question about this? So you see that we can invert the unilateral Laplace transform of rational function, just like you invert for bilateral Laplace transform, and here you always pick the RLC to the right side, and basically you always get this UOT part. Okay, and let's see the next example. So you have big X of S equal to x squared minus 3 over s plus 2, and so once again this is a rational function, and we can do partial fraction expansion, but now you see that the numerator has more degrees than the denominator. So numerator has more degrees than denominator, so we just do a long division. So we say it's a plus bs plus c over s plus 2, and you do the division, and you find out your a and b is minus 2 plus s, minus 2 plus s, and c is what? So you do a long division to find ABC here. And then once in this form, then once again you can do the inverse and unilateral Laplace transform. So you just pick the RLC for being the right part. So RLC will be RES greater than minus 2, and so the minus 2 invert to this minus 2 delta function, and s invert to u1, and 1 over s plus 2 once again invert to e to the minus 2t u of t. And yeah, here we use this formula such that we have the singularity function being the t's derivative or delta function will Laplace transform to s to the nth power, and this is converging for all s, although this function itself is a very diverging function. Okay, and yeah, so we kind of go through how to do inverse unilateral Laplace transform in those two equations, in those two example. So you basically just do pick the RLC being the rightmost RLC, and do inverse bilateral Laplace transform, and or you can just do partial fraction expansion, which is you do partial fraction expansion and look up the formula to do the inverse Laplace transform. Okay, and now we go to the properties of unilateral Laplace transforms. Okay, so a lot of the property of the unilateral Laplace transform will be same as bilateral Laplace transform. But big difference is that there is no RLC, and also because unilateral Laplace transform only care for x of t for t greater than 0. So you will see that some property has a change that need to heavily change to emphasize that x of t equals 0 for t less than 0. Okay. And and also we see the initial and the final value theorem are male natural here because we had this x of 0 when t less than 0 requirement for initial and the final value theorem. And but for now, every x of t will be equal to 0 for t less than 0. Okay, so we see some properties. So the familiar linearity, you have x1 unilateral Laplace transform to big x1, and x2 transform to big x2. Then x1 plus bx2 will transform to a big x1 plus big x2. And so similar thing, you can shift in S domain. Where you have s minus s0, then you get the HRE to the s0t x of t here. And then time scaling here, so we see the first difference here. So time scaling, you get a factor of a here, so x of at, and you unilateral Laplace transform to the same thing 1 over a, big X of s over a, so you multiply a here, divide a here. But the difference here is you must have a greater than 0 because you cannot have time inversion here. Because x of t must be only have signal when t greater than 0, so you cannot time inversion to something that is you cannot have time inversion to maybe your t plus t greater than 0 part to t less than 0 part. Okay, so a needs to be greater than 0 here, and the conjugation is the same as before. X star of t equal unilateral Laplace transform to big X star and small s star. And convolution, we also see difference here. So convolution here, the formula is the same. x1 convoluted with x2 transform to big x1 times big x2. But here you need to have your small x1 and small x2 both satisfy all conditions. This is a unilateral condition that they are identical 0 for t less than 0. Okay, so this is important. And then there's this most important formula here, and it's the most different one. So dx dt will have a unilateral Laplace transform to the same thing, s over big X of s, but minus the boundary term x of 0 minus. We'll do a derivation more carefully later, and we'll see that this is actually the most useful formula here because this helps us to solve the initial value problems with unilateral Laplace transform. And so this HR boundary term x of 0 minus will correspond to the initial values, as we'll see later today. Okay, and then the differential property in the S domain is the same. dp gets ds, then it transforms to HR minus t here. And the integration in time domain is also different. So integration limit, you want to start from 0 minus because you only care about your time from 0. Okay. And the initial and the final values theorems look the same. It looks the same, but the condition here are a little shorter. So x of t now is automatically being less than 0 when t less than 0 because that's our assumption for unilateral Laplace transform. And but I also need to contain no impulse and still need to contain no impulse or higher order singularity at t equal to 0. Otherwise, you will be caught by this integration from 0 minus. Okay, and anyway, so then we have the same form x of 0 plus equal to limit x go to infinity, s of s times x of s, and x go to t go to infinity equal to s go to 0 s big X of s. And here we have some comparison to the bilateral Laplace transform. So those are the 8-O table. And yeah, you see the difference is that it had the ROC column as we know before, whereas here we don't specify ROC anymore. And also there was a time shift here, and there was no time shift here because the time shift might shift your signal to something that has signal at t less than 0. Okay, and yeah, so those are properties. Any question? And no question, then let's go to the okay. Yeah, let's go to the next one. So we have the convolution property. Let's talk about it. So convolution property for unilateral Laplace transform is very similar to a bilateral Laplace transform one, but we need this extra condition. As we say, we need x1 of t equal to x2 of t equal to 0 for t less than 0. So they need to start after t equal to 0. Okay. If so, then we have the same thing. Okay. So we know if x1 of t and x2 of t or 0 when t less than 0, then we can just use this equation, and the analysis will be same as a bilateral Laplace transform one. Okay, and so what does this mean when our x1 of t is x of t and x2 of t is h of t? And so first of all, we have h of t equals 0 for t less than 0, and that means we have a causal system. Okay. So if we want to use this convolution property to analyze the convolution property of unilateral Laplace transform to analyze our system, then our system must be causal because you need to satisfy this, and the input need to start after t equals 0, because for t less than 0, your input must be 0. And then we can have a property, so we can use this property to derive our integration property here. So integration property is this thing equal to this thing, and it says integration from t0 minus to t and x tau d tau, then this is exactly equal to the convolution between x of t and u of t. And so if our x of t satisfies this equal to 0 for t less than 0 condition, and u of t already satisfies this condition, then both of these conditions satisfy, and you can unilateral Laplace transform both of them, and multiply them. That will be a unilateral Laplace transform corresponding to this thing, and so this is big X of S times big U of S, and big U of S we know that is 1 over S. So it is 1 over S and the unilateral Laplace transform over big X of S. Yep. And so this is one example. So once again, we use the convolution formula to derive the integration formula. And but you see that this formula is the same as and this check out. So this formula is the same as the bilateral formula. So bilateral formula will also have the integration, but it is the same only. But the integration is starting from from 0 minus, and so this only work out when you don't have extra thing of x or t. Let's say the t less than 0 got cut off, and this integration only start from 0 minus. Okay, and there's another example. That's the differential equation system that described by differential equation. So we have this differential equation: d squared y of t dt squared plus 3 dy dt plus 2y of t equal to x of t. And the system described by this differential equation, and so we want it to be causal to be able to use unilateral Laplace transform. So there are two things, and the first is we assume condition of initial rest. Okay, so it's assuming condition of initial rest, so the system will be causal. And if we also assume x of t equals 0 and t less than 0, then will be good. Okay. But before we even know x of t, we can solve for the system function. So the unilateral system function, or just as before, you can do the unilateral Laplace transform on both sides. And so this is equal to big Y divided by big X. And so you can just read from here is 1 over this x squared plus 3x plus 2. Okay. So we know the system function is this thing, so just just like the Laplace transform one, the bilateral Laplace transform. Okay, and so we want to use the convolution formula to to write down the system function, to write down the output, and so now we have the input, and we have a good input. So this is input x of t equal to alpha u of t, and this satisfies this condition here. So our small h of t satisfies this condition because it's initial rest and it's causal. And small x of t also satisfies this, so we can use our convolution formula to find out that our big Y equal to big H times big X. Okay. And so we already have a big H here, and big S will be alpha over S. Okay. And so we just have alpha over S times this thing, which is also equal to s minus 2 times s minus 1. s plus 2 times s plus 1. So y of s is this, and so now we want to find, so this is big Y, and we want to find small y. Then as we say, we can just do partial fraction expansion into those three partial fractions, something over s, something over s plus 1, and something over s plus 2, and do the inverse Laplace transform of picking the RC always on the right side. So it's just this 1 over 2 minus e to the minus 1 plus 1 over 2 e to the minus 2, and all times u of t. Okay, so you see the y of t is this alpha 1 over 2 minus e to the minus t plus 1 over 2 e to the minus 2t u of t. Okay, so you see that this is same as the this is same as the bilateral Laplace transform, picking the RC being the right side. Okay, and okay, so this also coincide. This also agree with our analysis of bilateral Laplace transform. So bilateral Laplace transform, we will also do the same thing. So we have the system function, and then we'll have x of t, and then we'll have a big Y as this, and then we will say that we have a causal system. Then we pick the RC to the right side. Then it's a causal system, so the RC must be the rightmost RC. Then we'll inverse the Laplace transform back to this same signal. Okay, so unilateral Laplace transform and the bilateral Laplace transform give us the same answer here. But we need to remember that this only works when both this convolution property only work when both x1 over t and x over t are 0 for t less than 0. Okay, and we have some textbook problem that show you how things are different when some of them don't satisfy this condition. Okay, and yeah, so you see that this all makes sense because when they are both 0 for t less than 0 means it's causal, and it means that you pick the RC being the rightmost RC, and when you do Laplace transform, then when you know it's a causal system, you also pick the RC being the rightmost RC. Okay, so I'll check out. So for this example, using unilateral Laplace transform and the bilateral Laplace transform is the same. It just give you different notation. Okay, and finally, let's go to the most important property here, the differential property. And the differential property, let's first do the derivation. So let's see how we get this weird boundary term. How we get this is we do integration by part. Okay, so integration by part says that integration of I also actually using a pen. Okay, and I guess then that's not okay. And okay, so the integration by part says that integration u dv equal to, okay, so this is actually dx. Okay, that was spaced. Dx of t. Okay. So integration by part says that the integration of u dv equal to uv minus the integration v du. And what we want is the unilateral Laplace transform of dx dt. So this is a unilateral Laplace transform formula, so you have dx dt here, and the integration, and then multiplied by s to e to the minus st then dt. And you do integration by part because you combine the dx dt with dt, so you think it is dx, and then you have extra factor of e to the minus st here. So this e to the minus t is our u here, and the v is our x over t. So you have this u and dv because dx dt times dt equal to dx, so that's dv. And so once you know our u and v here, then you just write down everything. So so uv is e to the minus t and x of t, and you need to write the substitution of boundary. So boundary at t infinity minus t0 minus, and then you have the extra integration minus the integration of v du. Okay, so here we do a little calculation here. So v, as we say, is x of t, then you have du. So you have a dx of e to the minus t st dt. Okay, so I guess I should try to write here. So d e to the minus st equal to, so we do a similar thing here. So this is equal to minus s and times e to the minus st dt. E to the minus st and dt. Oh, actually, let me try to find my pen. It's probably in my bag. See, it's here. Okay, so a little review of calculus here. So here we want du. Du we get, I guess, what we want to write is d to the minus st dt by calculus equal to minus e to the minus st. And so you move this dt to other side, so you have d to the minus st equal to minus s e to the minus st dt. Okay, and so you have this minus s here, and you have this minus sign here, so it becomes plus s here. Okay, and yeah, so you get in the end you got this plus s, then integration x of t e to the minus t dt. Okay. And then you look at things. So this term is this term. So you have s here, and this is exactly the unilateral Laplace transform of x of t. And then you look at this term, and t equal to infinity because of this e to the minus st. This equal to 0. Yeah, t equal to infinity. This e to the minus st decays and it becomes 0. And so you're left with this minus 0 minus term. So the 0 minus will x of t equal to x of 0 minus, and e to the minus st becomes 0. Become 1. So it's just minus x over 0 minus. Okay, and yeah, so this derivation, you have this integration by part, and you see that you get an extra term here. Okay, and okay. And then you can even concatenate this or recursively apply this formula to get the unilateral Laplace transform of dx squared, d squared x dt squared. And so you apply this formula, excuse me, and so you have s times this thing for dx dt. Yeah, so that's d dt of x prime of t, and you know x prime of t already transformed to this thing, and so you have s multiplied by this thing. Okay, so this s multiplied by this thing, so s times s of x, s times big x of x, s times big of x, so s squared big x, and s times x of 0 minus. And then you need to minus x prime of t at t equals 0, and so that's just x prime of 0 minus. Okay, and let's see a few examples here. We have time. Okay, maybe yeah. So I guess give you, hopefully don't confuse too much, but give you a little intuition about this x over 0 minus, and why does this corresponding to you cut off your unilateral Laplace transform in the 0 minus. So let's say we have two sets of x over t transform to big X of s, and dx dt transform to x over big X minus x at 0 minus. So let's say our first function is our unit step function, so u of t here, okay, is black line u of t, and we know it unilateral Laplace transform to 1 over s. And then you know that it has a singularity here. Okay, u of t, if you do differentiation, is delta of t. Okay, and delta of t will be picked out by the unilateral Laplace transform because, well, unilateral Laplace transform pick out the singularity at t equals 0, and it should transform to 1, and you see that it check out with this formula. Because s times x of s is 1, is s times 1 over s equal to 1, and minus x at 0 minus. So this u of t at 0 minus is 0, and so it's 1 minus 0 is 1. Okay, and this check out. But okay, then let's see a funny example of what if we shift our u of t, time shift our u of t to u of t minus t plus 1. So it's a function that will get cut off by unilateral Laplace transform a bit. So u of t plus 1 is this red line here. It's a unit step function starting at t equal to minus 1. And its unilateral Laplace transform is the same as u of t, because the h1 minus part will be cut off, and so unilateral Laplace transform is also 1 over s. But then dx dt then is here, but it's losing a singularity at t equals 0. So its unilateral Laplace transform is the same, but the derivative, the unilateral Laplace transform's derivative is not going to be the same, because its derivative is delta of t plus 1, and it's a spike at minus 1. And this spike will not be picked up by the unilateral Laplace transform integration. And indeed, you see that you apply this formula, the s of s times the big X of s is still 1, but you need to minus x at 0 minus, so you need to minus 1 here. Okay. So the difference here is this minus 0 and minus 1, because those two functions has different value at t equal to 0 minus. And you see the 1 minus 1 here is 0, and the same as our expectation. So the boundary term told you that your differentiation don't contain impulse here. Okay, so things check out. Okay, and finally we have about 10 minutes, and we can talk about differential equation. I guess the differential equation. Differential equation with initial condition, so initial value problems. Okay, and so basically it's same as the previous example. So previous example, when we talk about convolution formula, we had this differential equation, and with input x of t equal to alpha u of t, and and we solve for the its output. And but now we change from initial rest condition to initial condition, and there are those conditions. Okay, so our initial condition says that at initial time, which is in convention usually t equal to 0. Okay, because our unilateral Laplace transform and t always calculate at t equal to 0. So we'll set the initial time at t equal to 0, and at t equal to 0, then we have two initial conditions. One of it is our output, so we say our output started on beta, and also we have a derivative of the output. And how many derivative we here, once again, depends on how many order we have on this y. So the more derivative of y here, you need to specify more initial condition. So here we have a second order equation, and so we need to have two initial conditions. So y of 0 and y prime of 0. So dy dt is 0. And here we just say some number beta and gamma. Okay, and so what do we do here? So what we do here is we apply unilateral Laplace transform on both sides. Okay, and so unilateral Laplace transform on both sides, and x over t unilateral, so it's a very nice function. So it's just like a bilateral Laplace transform to alpha of s, and so the d square y dt square. Well, unilateral Laplace transform to a very complicated formula is this formula we talked about before. It is s squared big X of s minus s of x0 minus x prime of 0 minus. Okay. And it's a bit confusing because we write big X here, but actually we are transforming about y, so actually we should write y here. So it should be s squared and big Y, and minus s and y at 0 minus. But we know y at 0 minus is beta here. So we see how we use the initial conditions to satisfy to fill out terms in our unilateral Laplace transform, because the derivatives are give boundary terms, and the boundary terms are specified by these initial conditions. Okay. So s of 0 minus, so y of 0 minus is exactly this thing, beta here. And we also want the y prime of 0 minus, and it's gamma here, so minus gamma here. And so similarly, dy dt, so you have 3 times dy dt, and the dy dt we know is s, and big Y of s minus y0 minus. And so it's the same thing. So 3 times s, and so this is big Y minus y0 minus, and so that's minus 3 beta. And finally, this 2y just transform to 2 big Y. And all this is equal to alpha over s. Okay. Any question? So this is, I guess, the most important part. So how you do solve the initial value problem is you do unilateral Laplace transform on both sides. And when you have those higher order, when you have those derivative on y, you will get, I guess on x you also get derivative, and you also need to fill the boundary. But anyway, so you have those derivative on y. You have those derivative on y, and then you need to find all those boundary terms through the initial condition. Yeah, so then those y of 0 minus or y prime of 0 minus or even higher order term. Then you plug in the initial values. Here just the initial value is number beta and gamma. Okay, and once you have this, then well here you basically done, right? So you can write your big Y. So you have some function of you have some formula of big Y here. So you only have first order of big Y. So it's big Y times s squared plus 3s plus 2. So actually just as before, just as the previous example with the initial value. So you have a y times this s squared plus 3s plus 2, then equal to this initial term, so alpha over s, and 2 boundary terms. So you have beta times s plus 3 here. Okay. So you have beta times s plus 3 here, and you move to the right hand side. So it's beta times so minus beta times s plus 3. Move to the right hand side. So beta times s plus 3. And then divide by your s plus 1 times s plus 2, and then also the gamma term is just a gamma here, so just a minus gamma here, move to the right hand side, so you have plus gamma here. Okay, and yeah, so everything is so you have this alpha over s and plus gamma plus beta times s plus 3, and everything is divided by this s plus 1 times s plus 2. Which is equal to the s squared plus 3s plus 2. Let's write that down. Okay. So s plus 1, s plus 2 equal to s squared plus 3s plus 2. Okay. And yeah, and then we basically solve our equation here. Then from here you can plug in alpha, beta, gamma, or you can even not plug in. Then you can do partial fraction expansion and solve for your y. Okay, but before we do that, let's talk a little bit. Okay, so people like to give names to this thing. Okay, so this unilateral Laplace transform y, you can kind of look at the two parts. So it has this part that depends on beta and gamma, and it's plus another part that depends on alpha. And now we need to remember a little bit about what's alpha, beta, and gamma. So alpha comes from your x over t. Okay. So this alpha term is proportional to your x over t, proportional input. And so this term is called zero state response. And so this alpha term is your only output when your beta and gamma equals 0. So that's why it's called zero state response, because that's when your initial state is set to 0. So you set both gamma, beta and gamma to 0, and then you get this alpha response. Okay. And the interesting thing is this is also same response as what we solved in previous example. Okay. Yeah. So this is also same as when you set the initial condition equals 0. Okay. So the same as when you set this as the initial rest system, and then we'll get this. Yeah. So if you have your condition and initial rest, and your x over t also start at t equals 0, then your zero state response will be same as zero state response will be same as your causal LTI system response. Okay, So the zero state response will send us this initial response if your x of t star at t equals 0. Okay, and so this part is the zero state response, and the beta and the gamma part we also give a name. So the beta and the gamma part we call it a zero input response. You probably very intuitive. It's just when your input is 0, so your input is 0, you say alpha equals 0, then only get a beta and gamma part. So you have a zero state response and a zero input response, and they correspond to either your input is 0 or initial condition. This input, this the initial state or initial condition equals 0. Okay, zero state and zero input, and we see that for our constant coefficient, linear constant coefficient differential equation is it has this nice property that we didn't prove, but you can kind of imagine very easy because it's very linear. That your response is just a sum of your so this part is the zero input response plus the zero state response. Okay, so the response is just this part plus this part. Okay, which correspond to the response to input and the response to initial condition. Okay, any questions so far? Not. Then let's finish solving this. So we have our equation here. Our unilateral Laplace transform, well, s equal to beta times rational function, gamma times rational function, and alpha times rational function. And so if you pick a specific alpha, beta, gamma value, then we can do partial fraction expansion. So here we have some arbitrary value here. We can do partial fraction expansion and invert do the inversion of unilateral Laplace transform to obtain your time domain signal. So here we pick a very particular alpha, beta, and gamma. So pick alpha equal to 2, beta equal to 3, and gamma equal to -5. And then we do partial fraction expansion to find our y over s equal to 1 over s minus 1 over s plus 1 plus 3 over s plus 2. Okay. And a very quick check, it makes sense because you have s factor here, s plus 1 factor, s plus 2 here, factor here, and you have s plus 1 factor, s plus 2 here, plus 2 factor, and s plus 1 factor, s plus 2 factor here. Okay, so you write down your y of s as a partial fraction expansion, and you invert this like the bilateral Laplace transform by picking the RC always on the right hand side. So you always get the u of t term, and once again 1 over s is just 1, and 1 over s plus 1 is e to the minus t, and this 1 over s plus 2 invert to e to the minus 2t. And so y of t is just this y minus e to the minus t plus 3 to the minus 2t u of t, and this is for t greater than 0. For t less than 0, I guess unilateral Laplace transform doesn't tell us too much, but if you kind of some initial rest, then you can say it's 0. And and I guess for this initial value problem is also it's complicated when you have beta and gamma not equal 0. For t greater than 0, we have this thing. Any question? If not, we have 1 minute, so let's go over a quick summary. So here is a quick summary of the chapter. So we define two transforms. So we have the bilateral Laplace transform, and we see that the generalization of Fourier transform, where the integration variable is not restricted to j omega pure imaginary. So we have this whole S plane. And we see that on this whole S plane, we need to specify its ROC region of convergence. And actually, this polynomial plot and ROC tells us a lot of our system. And also, we define this unilateral Laplace transform, and we see that it can be used to solve differential equations with initial conditions. Okay, so just in time. And see you on Friday, and we'll go to next chapter about the Z transforms, which is for discrete signals.